Now, let us go through an example, then it will become very clear. This is a very this is an example that we have slightly modified, that we have taken it from T.Y. Lane and Burns, and this is a 2-span continuous beam which has an effective prestressing force of 1200 kilonewton, and you can see that at this locations you have a constant eccentricity of 150 millimeter, and it has a linear profile here, and here you have a parabolic profile. So, as we have the very first beginning we have discussed about how to get the equivalent. Just by looking at the cable profile, you can quickly show prestressing is designed in this 2-span system to take care of this. It is going to create an uplift force at this location, and it is going to create a uniformly distributed load like this in this span, right. In addition to that, what is that you are going to have? In this location again I am going to create a moment MP which is equal to P into U. These are the loads that are generated because of this profile. See, this is a linear cable profile, that is why you have a point load which is pushing, and we have seen that it is going to be P into theta, the slope change, right. So, quickly you can find the loading diagram. So, for example, this one also you can find out the loading diagram, okay, easily by creating what is the eccentricity that you will have, right. So, and then you can design the system. Here the slope change is again 0.16. So, each of them span is having 30 meters, and now quickly we can calculate the M1 diagram. So, the M1 diagram at different locations you see here. At support A, I have a positive eccentricity, again eccentricity will be positive. If it is measured downward, it is positive, here it is negative. So, this is your CGC, right. So, this is for eccentricity, right. So, that is the reason 0.15 is considered positive, but the moment it will produce should be positive eccentricity is assumed to produce negative moment. Why? Because we have discussed previously that prestressing moment should always be opposing the load that is coming from, or moment that is coming from your external load. So, that is the sign convention that we are taking. So, it is going to take minus 180, and then you have at location D you have eccentricity of plus 0.4, that is creating a prestressing moment of minus 480. At location B I have eccentricity of minus 0.4, that is creating an eccentricity of plus 480, and I have at location C I have eccentricity of 0.4 plus 0.4, basically at this location. Sorry, this is at this location, this is not exactly at C. Let us say this is at A, B, C, D, maybe E I should say, right. And this is at minus 480, and of course, at this location there is no eccentricity, so it is going to be 0, right. So, at C it is going to be 0. So, this way I can establish my M1 diagram, which is a primary moment diagram, right. So, these are the things. So, we plot this, okay. So, we are just plotting it on the scale, minus 180, minus 480, and then plus 480, minus 480, let us call this a C, right. So, you get at C is this 0. Now, I want to establish the loading diagram. See, loading diagram quickly, as I told, from equivalent load also you can create, but let us say for more generic case quickly we can generate. Now, the whole idea is we want to find the entire loading distribution, so that I can do moment distribution to find out the actual entire I should say M2 diagram, which is summation of M1 plus M1 prime directly. So, M2, to find M2 from moment distribution method, I need to know the loading distribution on the beam. So, loading distribution we are doing it in an indirect way, okay. So, from first we calculate M1 diagram, then we calculate the shear diagram. From shear diagram we are going to get the load diagram, okay. So, let us look at it. Now, we are going to plot the shear diagram. Now, shear diagram, we know that V is equal to dm by dx. Now, shear at A is going to be the moment at D minus the moment at A divided by the distance between them. Now, moment at D is minus 480, moment at A is minus 180. So, when you subtract them and divide by the distance 15, you get the shear of minus 20 kilonewton. For the span DB, now you see here, again we go through the same process. VD, the shear at the location D is going to be the bending moment at the location B minus the bending moment location at D divided by the distance between them. So, that is 480 minus 480 by 15, which is 64. So, the shear has gone from negative to positive 64 at the location D. That means that there is going to be a vertical load, you know that is going to be summation of 64 plus 20, because the difference is an 84 kilonewton. So, that we will see. So, for BC, now that we have found out the shear distribution at span AB, now let us look at how to get the shear diagram for the span BC. So, we are getting only the slope change, right. So, we are doing the linear transformation of the cable, an approximate cable profile equation is used, which we are taking this as a. So, basically this support, if I linearly shift it somewhere here, the entire thing is going to shift by the same magnitude without changing the curvature. So, this eccentricity now will become 800. Okay. So, that is what we are going to use. So, instead of going like this, okay, like this, what we are doing is this portion we are bringing it here. So, this the entire thing will shift by same magnitude without changing the curvature of the cable profile. That is what we are doing. Okay. So, if you do this approximate thing, moment at M1 is going to be, again from parabolic equation, we know that it is 4 PE x by L square into L minus x. Now, shear is going to be dm by dx. So, if you differentiate it, you get 4 PE into E L square by L minus 2x. Okay. Now, at B, at the midspan location, right, at B, if you put x is equal to 0, you get minus 4 PE into E by L. Now, what should be the eccentricity? Now that I have linearly transformed the cable profile for quick approximate calculation without changing the curvature of the cable profile. So, this will be PE into E is nothing but your moment at these 2 points. So, you can see that it is going to be 480 plus 480, that is the total summation, that divided by 30 will be the length, then you get a shear of negative 128 kilonewton. Now, the difference of shear between C and B is given from change in the slope of the M1 diagram, that is already given to you in the problem. That change in the slope is 0.16 into effective prestressing force PE here. So, which is 192 kilonewton. So, from B to C, the shear change is 192 kilonewton. So, what is the value of shear at C? It is going to be 192 minus 128, which is 64 kilonewton, right. The shear at C is going to be 198 minus 128, which is 64 kilonewton. So, we can plot all of them. So, basically this is what it is. So, this is the location, I mean, we have note that is G. So, you see here, this is the shear diagram. Now, what is load diagram? Load W is again dV by dx. So, again you can, now that we have established the shear diagram, I can quickly calculate your load distribution for this also, right. So, if you see this, we need to equivalent load diagram, we need to, of course, there is a eccentricity at the left end. So, we have to include the moment due to prestress 150 kilonewton meter at A also. Now, what is the point load at D? 64 minus of minus 20, which is 84 kilonewton, which is pushing up, right. Now, since B is a reaction point, this is one thing you need to, that I will directly go to the support, right. So, the downward load at B need not be considered. We are looking at what is the load distribution on the span plus the moment at the end, but we do not consider the reactions that it is being going to the support. Now, for this shear diagram, you can see this is the moment that is due to prestressing, this is a load vertical thrust that I am pushing on the beam, and this also you can correctly calculate from P into theta. So, that is also possible. This 84, the W at this location is this. Now, I have a constant shear profile in the span BC. So, you know that difference in shear is 128, 64, sum them up and divide by 30, you will get constant load of 6.4 kilonewton. If the shear diagram is linear, my load diagram is going to be constant, which is distributed load of 6.4 kilonewton meter. This way, I can get now for an 2-span continuous beam the load induced by prestressing. Now that I got the load, I can go ahead and do moment distribution to directly get my EM2 diagram. So, let us see how do we do the moment distribution method. Okay, so this is the loading. So, you see here 180 kilonewton meter, it is positive, sorry, it is a counterclockwise moment, and here a load of 84 kilonewton, 6.4 kilonewton meter. So, of course, I think this is an advanced course, and you must have studied moment distribution in your structural analysis course, or also you can look at the videos of moment distribution in other NPTEL courses. So, first step what we do in moment distribution method is we assume that the joints to be locked and calculate, if I prevent the rotation and these supports, how much is the fixed end moment that will develop. And you can see the loading here is all upside down, right. So, the rotation here I am going to develop positive moment and here I am going to develop negative moment. What are the values? W into AB square by L square, right. So, here everything is symmetric. So, A and B are 15, 15. So, 84 into 15 into 15 square by 30 square. So, left support I am going to have plus 315 and the right I am going to have minus 315 kilonewton meter. Similarly, for the span, okay, this is A, this is B and this is C, right. So, for BC now my load is WL square by 12, which is plus, and this is minus, which is 480 and minus 480. These are the fixed end moments, right. And as you can see, the end A is a hinge support, it is not going to take any moment. Similarly, the support C as well. So, we need to balance only that intermediate support. Now, when you look at it, of course, this also has a load of minus 180 that is coming from here. So, this is always there, right. So, this is only this. So, this load is always it's going to be there minus 180. So, when you add all of them minus 180 plus 315 minus 315 and then right. So, this is an externally applied moment due to this will always be there, right. Only you are balancing only the rotation that is induced by the load that is acting on the span, right. So, what is that we do? Now, you see here how much this joint B on the left and right side they do not have equal moments. So, the difference is basically if you see here it is going to be 165 kilonewton meter, which is positive excess. So, I have to balance the joint in proportion to their distribution factor. Here it is spans are all same. So, distribution factors are 0.5 and 0.5. So, 165 has to be balanced, it is having excess plus 165. So, I need to apply minus 165 and I put 50-50, right. So, that is how I get minus 82.5 and minus 82.5 balancing it. Similarly, this is a hinge joint, I have to balance only the fixed end moment, which is plus 315 I have. So, I am balancing it by minus 315. Similarly, at support C, I am having a moment of minus 480, I need to balance this by applying a plus 480, because it is a simple support, everything has to be balanced, right. So, you get this step. Now, you see here, now the next step we have balanced, the next step would be to carry over. Now, carry over moment will be done to the locations where you have fixed support or continuous support. So, from A I have to carry over to B, BA. Similarly, from C I have to carry over to BC, right. So, how much do I carry over? Half of it, 315, half of that is minus 157.5, half of 480 is plus 240. Though we have balanced at this location, because now I am carrying over this moment, again the joint has become unbalanced. So, now how much is the total unbalanced moment that I have? You see here, it is 2.5 plus 80, basically it is 82.5 plus 82.5 is excess. Now, I have to provide a minus 82.5 and I am proportioning that minus 82.5 50-50, which is minus 41.25 and minus 41.25. So, now that we have balanced, now I do not need to carry over anything to support A or C because they are simple supports, they are not continuous supports or fixed support, right. So, now we have balanced it. So, when you add all of them, so this and this will get cancelled, but still you have a moment of minus 180, that will still be there, and when you add them up you have minus 596.25 and plus 596.25 and I have a moment 0 here, right, because there is no externally applied moment from prestressing. So, that is why here this joint will be balanced, here you will have minus 180 and this joint left and right will be balanced, but they will have a bending moment, right. So, in this way, so these are the moments we are directly getting, which is M2, which is actually M1 plus M1 prime, we are directly getting from moment distribution method, okay, MDM. So, when you plot this, you get minus, of course, minus 180 and 596, minus 452 and 0, right. So, you can use your, when you draw the bending moment diagram, obviously you have to follow the sign convention. Typically, we take this as plus and this profile is taken as minus, right. So, you follow the bending moment diagram depending upon the left and right. So, you get the bending moment distribution like this. This is your empty diagram. So, directly once you know the load distribution from prestressing, you can do the moment distribution directly, get your M2 diagram. Or the other method that I told you is the superposition method, that for even for this 2 span we could have done it, because I can easily calculate my upward deflection that is produced because of the prestressing, and then I can calculate the reaction that is required to make the deflection to 0. So, that is also, it is easy to do for simple 2 span structures, but not difficult, but it becomes difficult for more number of indeterminacy, right. So, but the moment distribution, you know, it's a very straightforward, very elegant way of solving an indeterminate beam. Okay, now we have done this moment distribution. Let us look at the values of EC. Now, what are the values of EC? This is the location of your thrust line or pressure line. Okay. Now, you see what is EC, which is M2 by P. Again, I am telling, for statically determinate system, there are no secondary moments. While you do the pre-stress, the location of your compression will be at the location of steel itself, right. However, in case of a continuous system, because you develop secondary moments, the EC will not be at the location of V, it would have shifted up. So, that is what we are going to look at now. The compression line, thrust line is M2 by PE. So, these are the M2 diagram that we got. So, you can see that the pressure line is nothing but M2 by PE. PE value is given to you, which is 1200 PE is, remember, it is 1200 kilonewton. So, everything when you divide by 1200, so you see here this is minus 180, and midspan location using free body diagram I can calculate this moment to be minus 422, and this is plus 596.25, this is minus 452 at this location, right. So, at E. Okay. So, these are all the things that we got, and when you divide everything by 1200 kilonewton, you get a moment of plus 0.15, right, and then you have plus 0.351 and you get plus 0.49. So, this is again, we have to get this will be negative, okay, and because everything has to be divided by, let us say, negative 1200, okay, let us put it that way, because what we have done is, again, you know, if you look at this, if this, right, CGC is below this, we take that as positive, if it is above CGC, we take that as negative. So, that is the reason, if the moment is negative, you divide it by negative PE, For every negative P, you divide by it, you get positive value. So, if it is a positive negative, you will get minus. So, that means negative 0.49 means the location of compression line is above the CGC. So, that is what we are trying to say, right. So, this is plus 376, which is also good. So, you can see here that 0.351 is at the midspan. So, you have to, it has shifted up. So, this is the location of your pressure line. So, if it is a statically determinate system, again while you transfer the prestress, the pressure line will coincide with that of the CGS. Because now I have developed some secondary moment, the pressure line now has shifted up, okay, and it is causing some changes in your bending moment distribution. So, you not only have M1, you also have M1 prime. So, you need to use M2 diagram for your design. Secondary moments cannot be ignored in the design calculations, because secondary moments can actually it can offset the design. So, that is what we are trying to tell. So, we have to be very, very careful. So, basically for example, the positive benefits on the span locations will be reduced because of the secondary moment, but most of the time the negative moment demand when you design for it, it will come down. Okay. So, one way secondary moment is beneficial, but at the same time you cannot say for all locations. Generally positive locations it will increase the demand, for negative location it will reduce the demand. So, we need to account for it depending upon the cable profile that you have. So, secondary moments cannot be ignored in your design calculations. Okay, now let us look at what is the effect of pre-stressing and loading on a simple portal frame. So, I have taken a simple portal frame and it is subjected to some external load like this, dead load plus live load like this, dead load plus live load, and you see here I have a column which is a hinge joint both sides, and I have a girder with some eccentricity which is a parabolic girder. Now, here the CGC of the section is varying, though the cable profile is linear. Similarly, you have here eccentricity E equal to 0, here you have some eccentricity, right, and similarly here you have some eccentricity. So, you have the eccentricity varying because the concrete section itself is varying, right. Now, let us look at what is the effect of each individual case. Now, this is the, when I do the pre-stress, I am going to create an upward force, right. So, here you see here the cable profile, though it is linear, now because the CGC is varying in a parabolic way with respect to the cable profile. So, you create again a distributed upward load. So, that is what it is here. Now, when it is distributed upward load like this, when you have a hinge support, what will happen? The beam will try to bend upward. In that process, it will try to go in like this, but the reaction will pull it up like this. Okay, reaction will pull it up like this because the beam wants to go up. So, in that process, the support will try to go inside, but the support will not let it go inside. So, it will develop reaction in the opposite direction. That is the equivalent load because of the pre-stress. Now, let us look at what is the, if I take only the axial component of the pre-stress, you see here. Now, again there will be a shortening that will be happening in the elements. So, my system is going to deform like this. So, you see here both sides you have axial shortening that is happening due to the pre-stress, and because of that again the system wants to go inside. So, the reaction will be pushing it outward, right. So, here also the reaction is pushing it outward, right. So, let us look at the next case. So, this is from the vertical equivalent load, this is from the horizontal axial component of pre-stress. The next one is because of the superimposed dead load and live load. What will the dead load and live load will do? Dead load and live load will try to push the beam downward, and because of that the support will deform like this. Now, the column wants to actually go out. Now, I am going to develop reaction like this, right. So, it is going to develop reaction like this. For a typical gravity load, this is how you will get, right. Now, when you combine the pre-stress and dead load, you will find that only because of the pre-stress and the dead load effect, you will find that still you will have some vertical reaction that will develop, but still the reaction will be the same way as you have it for a pre-stress. So, still the reaction will be actually preventing the support from moving inside, still it will be outward reactions only you will have. Now, when you have combinations of pre-stress and dead load and live load, now these reactions can be quite significant, right. So, the reaction can be quite significant. So, when you add the pre-stress, dead load and live load effect and moment will be high, then the net reactions will become similar to that of what you have for superimposed dead load and live load, and the deformation will become like this. You see here, right, because now this all this equivalent load will get nullified. Typically how much, the pre-stressing we try to balance maximum of 80 to 100% of dead load only. When you design the pre-stress, you try to balance only 80 to 100% of dead load. So, now only that is the reason, only when dead load and this is occurring, the reactions are like this. But the moment your live load becomes also acting, then your pre-stressing effect will get somewhat nullified, the vertical component, then you will have the reactions and bending moment will be similar to that of what you have for your superimposed dead and live load. Okay. So, this is what a tertiary moment is. So, this let's understand what a tertiary moment is. It is a very simple portal frame that you have. Now, portal frame can have members with the different direction. Here you have a simple portal frame, a horizontal member and a vertical member, and pre-stressing of tendon can create an axial contraction which can induce tertiary moment. So, for example, when I am doing tension pre-stressing like this, it is going to push this vertical members A, B and C, D inside, right. So, it is going to, or when the member is trying to shorten, in other words, the column A, B and C, D will prevent that shortening that is happening to the member B, C, right. So, let us look at it. So, what are the main effects of this tertiary moment? There will be a reduction in magnitude of pre-stressing force in a particular member due to the restraint of the additional members. Now, when I am trying to squeeze it, these members will prevent that axial shortening in a way, it will offer resistance. So, the net effect of pre-stressing on the horizontal member will get somewhat reduced. The development of tertiary moments due to the bending deformation of the indeterminate structure due to axial contraction has to be considered. Okay. So, now how do we consider that? We will explain that through an example problem. So, this is also basically you see here when that axial deformation is happening, now the vertical members will undergo some additional moment which is similar to the moment that are generated because of the support settlement. So, something because you have a chord rotation that it is happening for the vertical member, you will develop some moments in the same direction. So, that we will see how do we include that. So, those effects sometimes may be small, but we cannot ignore them. We have to do the calculations depending upon the geometry and depending upon the amount of pre-stress that you have. Those tertiary moments can sometimes become high and it can create negative effects in your design. So, we need to ensure that those are accounted in our design. Okay, let us look at it now. Tertiary moments, you see here this is what simple portal which is A, B, C, D, and now you see here if you do some simple assumptions, with that also we can find out what are the relative load contribution that is happening between PBA, which is a axial load that is taken by this vertical element, and PBC. So, basically PB, this should be PBC, right. So, which is this. Now, if you assume this simple thing to be like a cantilever and it is subjected to an axial load, let us say PBA, and it is deforming, laterally deforming by delta, the same delta from compatibility is what it is happening, because it is this is what we said, this is going to go like this, and similarly this is what it is going to come like this, and this is what you are going to have. So, this delta at both locations have to be compatible, right. So, that is what we are saying, this delta, and if I take only half of this member, that deformation, because on the other side half is being resisted by the right side support, right. So, this delta, the deformation that is happening in the half of this BC should be equal to that of what is deformation that is happening in the member AB, right. So, for compatibility, that is what we are saying, the lateral deflection delta of the end of the column AB should be equal to the axial contraction of 1/2 of the transform BC, right. So, if you make this assumption, we can find out, because I am going to have some chord rotation that is happening here like this, like this, right. So, you get 6 EI delta by L square. So, this is the moment that will be developed because of the support settlement. Similar thing that will happen, and we need to account for it. So, if you make this assumption, right. So, for delta, for let us say if you assume this like a cantilever, it is going to be PLQ by 3 EI, that is a delta for the column member AB. If half of that beam is undergoing this axial contraction, and let us say that that is the axial load, then it will be PL by AE, and now L I am considering LBC by 2. So, it will become PBC into LBC by 2E ABC. So, I can find the relative load taken by the axial member BC and the column member which is BA. So, if you do that, you can come up with a simple expression, because the delta has to be same, and you can find out the relative stiffnesses in this way, which is this 1.5 LBC into IBA by L cube BA by times area, which is ABC. Okay. So, let us explain through an example problem. This is again a simple portal frame. I am taking this beam as 12 meter long, and columns are taken to be 6 meter tall, and I am applying an effective prestressing with this cable profile, a linear cable profile. Okay. So, the moment whatever that I am having in this joint, they will balance, okay, due to prestress, they will be, so they will get balanced, and I am assuming concrete strength is 40 megapascal, and here you can see, okay, in this example I have taken it as 5 meter. So, let us see what I have used in the calculations. Okay. So, this let us say 5 or 6, but this BC is taken as 10 meters. Okay. So, let us say the beam cross sections are 400 by 800 mm deep, and columns are 800 by 800 mm, and they are having eccentricity of 300 millimeter towards outside of the frame at B and C. Now, BC, which is prestressed by a parabolic cable with an eccentricity of 300 millimeter above the centroid at B and C. So, this is above, right, and at positive location again you have an extra centroid of 300 mm. So, now let us look at what is happening. Okay. Okay, I have taken 12, right. Okay. So, this has to be 6 and this has to be 12. Okay. So, let us go ahead and let us look at the calculation. So, area of this beam BC will be 400 by 800, which is 3,20,000 millimeter square, and IAB, which is the moment of inertia of the beam, which is 800 into 800 cube by 12. Okay, this is for the column moment of inertia, which is 3.41 into 10 to the power of 10, and as per the equation from the compatibility condition, we derived, you see here, the load that will be taken by the column, which is PAB, to that of column load that is taken by the member BC, which is beam, you find that the ratio is only 0.0088. So, you can see that means the load that is taken by the vertical member is so negligible, it is only about close to 0.9%, very small. So, for all practical purposes, we can say that the entire prestressing force is assumed to be resisted only by the axial member BC. Okay. So, that is what we say. So, this can be different. For example, if you look at let us say you have a wall inside of a column, then the moment of inertia can be so high and this number can go, then your ratios will play. But for this portal, I have a column and a beam. So, for such kind of portal system, when you do post tensioning, invariably the beam will actually feel all the axial force, but it will not be taken care by the vertical member, though the lateral load effect will be there. Okay. So, that is what we are going to look at. Now, what is the elastic modulus of the concrete? 5000 square root of FCK. So, we take 31,623 megapascal. Now, the deformation is for this half the member that we take, which is going to be PL by AE, and now L is LBC by 2, half the length only we consider. So, the load is 3000 and I converted it to 1000 and 12 meter becomes 12,000, and you substitute all the numbers, you get your delta as 1.77 millimeter. Now, why this delta is required? I need to calculate what are the fixed end moments because of this lateral deformation or the chord rotation that is happening in the column, right, which is 6A delta by L square. You get the moment is 293 kilonewton meter, which is not small. So, we need to account for that. So, that is the reason it becomes important to consider this moment that is happening from the. So, the moment distributions in the column member can get modified because of the axial contraction that is happening in the girder. Okay. So, now let us look at it. Again, the stiffness ratio, if you look at it, we need to do the moment distribution method. So, the moment can be distributed using moment distribution method. Again, I have to calculate the stiffness ratio. Let us assume that elastic modulus is all same. So, in this particular joint, when you look at it, so IB by L, so which is IBC by L, so which is I is this and L is this, then I by L for the beam, which is again 6 meter, which is 6000 divided by moment of inertia for the column is quite high. So, 3.41. So, you can see that the stiffness of the beam is 1/4 to that of column. Okay. So, that is what it is. So, you can either take EI by L, E is constant. So, that is why it is getting nullified. And now, we are going to look at the symmetry condition, and we are going to look at only half of the frame to quickly do the analysis. So, then the stiffness, if I take L as LBC by 2, then the stiffness will become further reduced into half. So, the ratio will become, instead of 0.25:1, it will become 0.125:1. So, that we can do moment distribution only for half of the symmetrical frame. So, this is all idealization that you can do. You would have learnt it in your structural analysis. So, I have to find now the distribution factor depending upon the relative stiffness of the members that are connecting in this one joint. So, we are doing only analysis up to this half, one half, right. So, I am interested in only in what is happening in this joint B, right. So, two members that are connecting BA and BC. So, DBA will become 1 by 1 plus 0.125, which is 0.88, and DBC will become 0.125 by 1 plus 0.1, which is 0. So, you can see here that for the lateral deformation effect, axial contraction, the column is in flexure, it is going to take lot more moment than the beam. But however, the axial load effect was taken more by the girder, right. So, again we have, now that we have found, we can do simple moment distribution method. Joint B has 0.88 and 11. These are the fixed end moment that we found at A and B, and this joint B has to be balanced. So, I have to apply plus 292.9, and then I am going to put it in the proportions of 0.88 and 0.11. So, that works out to be these numbers. Now that the A is a fixed support, now I am carrying over half of this moment, which is this, which is this. So, it becomes 128.9. So, when you add all of them, you get minus 164 plus minus 35 and plus 35. So, if you look at it on this joint, because of this delta, at A I have to take a moment of 164 because of pre-stressing. At B I have to take a moment of 35. So, it is not really small, especially if you look at this fixed joint A, 164 kilonewton meter additional moment that I am developing, that we need to consider in our design. But most of the time I have seen that the post tensioning, when people do it at a later stage, another contractor comes and then he does it, and they do not really explicitly consider in the design. So, we need to be careful. right. So, the tertiary moment is 35.2 kilonewton meter in BC and it varies linearly to 164 kilonewton meter hogging at A. So, that is what we have, and this is the moment distribution. This way we can consider the effect of pre-stressing and what are the moment that it is being coming to the vertical members in a simple portal. You can do that for multiple portal frames also, but nowadays the finite element softwares are available to calculate this effect, but we have to account for it. Sometimes knowing this simple analysis helps you to verify what results that software is giving. So, that is very important for us to know that, right. So, let us summarize what we have discussed in this part of the video. In this lecture, we talked about advantages and disadvantages of continuous system. More importantly, we understood why the secondary moments are coming in a continuous system and how do we get the moment due to pre-stressing in a continuous system. We have seen either you can use method of superposition for simple cases, or for generic case it is always better to use a moment distribution method to get directly your M2, which is a summation of a primary moment and secondary moment from pre-stressing. We also finally discussed the importance of tertiary moments and we solved one portal frame and we saw how moments are getting developed in the vertical members. So, thank you. So, we will continue the discussion in the next part of the module. Thank you.